Okay, so welcome to Enriched Finite Elements. This is going to be a very quick class. We're going to discuss the syllabus for the class, what we're going to look at. As you know, as a prerequisite for this class, you had to take the Advanced Finite Element Methods course, ME 46050, because we need all that knowledge to build on top, right? Generalized or enriched finite elements require the standard finite element as a prerequisites. So as you see here, I talk a little bit about the type of problems where enriched finite element methods are useful, and these are mostly problems where you have to deal with the geometry in a specific way for which regenerating finite element meshes is not feasible. It's either too complicated or too computationally expensive, so you need to find an elegant way to handle those problems, right? Problems in that category are, for example, when you are dealing with discontinuities, so you are dealing with very complex boundaries or cracks or material interfaces when you're modeling composites. When you don't know your boundaries of your problem, right? Let's say you're trying to optimize a geometry, and throughout that optimization process, the boundaries are going to change. So instead of recreating the mesh that you need for the analysis, you can find a smart way to transfer that complexity into the formulation instead. So that is what we do with enriched finite elements. In a way, we're transferring the complexity of the mesh generation to the formulation, yeah? And while doing so, we are able to obtain the same accuracy and the same convergence rates. You are all familiar with that. Okay, so the course learning objectives. This is what we're going to be able to do towards the end of the class. Discuss the different state-of-the-art enriched finite element formulations and identify problems where such formulations can be used. And we just talk a little bit about the types of problems where these type of formulations are very useful. Okay? Extend a standard FEM package to include enrichments. So the idea is that in this class you're gonna take the standard FEM package you already work with, and you're gonna add a part that is going to deal with all this enrichment formulation. Evaluate the different enriched methodologies and judge the performance on real problems. So we're going to look at several enriched methods, and I will discuss in detail about them in a minute, but the idea is that you really try to see how different enrichment functions work given a particular problem, whether this enrichment function is better than that enrichment function, and if it is, why is the reason behind that. Okay? Remember, we briefly touched on this during the Advanced FEM course, the idea of having your standard finite element space and augmenting that space with some information that you know about the problem at hand that could improve the solution, the approximation. So it's very powerful because you can pretty much add anything you know about the solution to reduce the error of your approximation. And you add that information through the so-called enrichment functions. Okay? Now, of course, there are some enrichment functions that work better than others. And we will also discuss all of that. And then use a software package to simulate complex problems that require an enrichment formulation, rich formulation. So the outline for the course is basically is going to be divided into two main parts. What is the generalized or the extended finite element method? So you probably heard the terminology DE-FEM or XFEM out there. And those are they are very well established already. These are formulations that have been proposed by Babuška in the beginning with the so-called partition of unity methods. And they have been developed to a state where they can be used to solve a lot of interesting problems. And we're also going to look at some of the stuff that I've been working on, which is also generalized or enriched finite element formulations, but with some things that are slightly different than DE-FEM. So we're going to look at interface-enriched formulations, And these are basically used to solve problems with discontinuities, particularly focusing on discontinuities like the XFEM, but in a different way, because where XFEM is placing enrichments to nodes of your original mesh, in these other methods, what we do is we place enrichment to nodes that are created along the discontinuities. And it turns out that this has a lot of implications, right, in terms of computational implementation, right? The implementation is simpler, and enforcing boundary conditions is also simpler. So we will look at all these different ways to enrich our finite element space to be able to improve the solution. So you have the XFEM, GFEM. We're going to look at that first. And within XFEM, GFEM, even though you can use this framework for let's say, have an equivalent to the P version of the finite element method. So you can have the P GFEM equivalent, where you are enriching your nodes of your mesh with polynomial enrichments. You can so this is basically, if you think about it, making your approximation more smooth, right? You're going higher in interpolation order. You can also apply this framework, and if you introduce an enrichment function that has a discontinuity, you can also apply the same framework to model cracks or problems that are really discontinuous, right? And then we will delve into this XFEM. XFEM and GFEM are exactly the same thing. It's just that today it is understood that XFEM is GFEM applied to discontinuities. That is the way today it is understood, okay? And now interface-enriched formulations, we will look at two methods, the interface-enriched generalized finite element method, or what we call IGFEM, which is only to model weak discontinuities. Weak discontinuities, I don't know if we discussed this at all in the advanced FEM class, but a weak discontinuity is a discontinuity in the gradient of the field. So think about a displacement field that has a kink, right? So that displacement field, the gradient, is discontinuous. So that is what we call a weak discontinuity. Now, you may think about what is a strong discontinuity. Well, what is the answer to that? What is a strong discontinuity? If a weak discontinuity is a discontinuity in the gradient of the field, a strong discontinuity is a discontinuity in the field itself. And so those type of problems are, I mean, if you think about fracture mechanics, all these cracks, then these are lying in that category of strong discontinuities. And for that, I also I'm going to discuss the discontinuity-enriched finite element method, which is basically an extension of IGFEM to include enrichment functions that take into consideration the strong discontinuity part, right? So you will see that this is really a nice, a powerful framework to the analysis of discontinuities. And of course, we will delve into the computer implementation of this, right? You will see that all the machinery that you have already built in the standard finite element package, without much modification, can be really adapted to use enrichments, right? And that is super nice, because you can take any existing finite element package, and with knowledge on how enrichment formulations work, then you can bring that extra capability into your standard FEM package, and then suddenly you have a way to analyze any problem with discontinuities, you know, regardless of their location inside the mesh. That is very powerful. But that said, I have a couple of recommended books here. Of course, remember that we're building on top of what we learned on PFEM. So there is the book of Szabo and Babuska here that I always give as a recommendation. And I also have this recommendation of a book of Tom Hughes. That's also a nice book. And we have the book chapter that, I mean, you know that we were writing a book with a couple of colleagues that is, the title of the book is Enriched Finite Elements, Methods, Theory and Practice. So we do have a chapter, an entire chapter that deals with XFEM or GFEM. And I am also working on my chapter on the interface enriched and the discontinuity-enriched finite element method, right? So those are going to be the sources for this. But of course, it's just to back up knowledge that we get from the class. So during the class, I expect to teach you everything that you need to know about these formulations and how they work, and how simple it is to incorporate that in your standard finite element formulation. The same way we did it with DE-FEM, where you have your linear shape functions, and then we stacked in the back, right, all these non-linear shape functions, the quadratic, the cubic, the quartic, and so on. Then we're going to do basically the same thing with enriched FEM. So we're going to have our standard FEM, and those are going to be added to a container. And then after that, we're going to add enrichment functions. And then the rest stays the same, more or less, with some changes here and there. Okay, but that is the idea. And we're going to have a project. I am still in the process of finalizing this project, but I can tell you now that it's going to have one 1D problem and one 2D problem. The same format as we had for the advanced FEM class. I think it's nice because if you have something that works in 1D, then that helps you build a lot of understanding about how these formulations work, and you can get all these convergence rates and do fancy analysis. But then I think having the two-dimensional problem also helps you in really applying this to something meaningful. So I'm looking at perhaps giving you a problem with a circular inclusion where you have to solve the problem with a finite element mesh that has nothing to do, it's completely decoupled from that circular inclusion. There is an analytic solution for that. It's called the SLV inclusion problem. And this is we have used it, this solution in many papers to basically test how our enriched formulations work. It's a nice problem. Of course, it's a challenging problem, right? But I mean, I am really hoping that you guys are with the knowledge that you built on standard FEM, I think it's going to go very smooth. And that's it. That's it for the syllabus. Of course, again, that final project, as I said in the first class on advanced FEM, if you do a good job and you are able to answer everything in that project, then I see no problem in giving you a 10 for this class. You know, I'm not in the position that the 10 should be forgot, right? As long as you do everything that is needed and it makes sense and it's nicely written in a report, I have no issue whatsoever in giving you a 10 for this class. Of course, to get the 10 is gonna take you some work, right? Well, the report I'm also looking forward. Here I have some notes on the presentation of results. It should be written as in a paper, right? In a way, this is going to help you prepare for the moment where you write your thesis. And then you have, I have a note on collaboration. And again, we go back to the same discussion we had in advanced FEM, where if you start to compare codes, right, then you went too far, because then you're not learning really. So you can talk, you can discuss as much as you want. You can create synergy. You can meet with your peers and then talk, and you know it's you get into very nice, interesting discussions. But the moment you start comparing codes, that's probably too far already. Okay. Okay, that's pretty much it, right? I will give you the details on the rooms we're going to be meeting for the next classes. Any questions on your side? Anything you wonder about the format, or you already are familiar with the format, the way we are recording the lectures, so they are going to be posted on Brightspace. Normally, just after the class, the notes, sometimes it takes me a bit more time to post them, but at least the videos are going to be there almost immediately. Any questions? Yeah?
So I actually have a question on the format of the technical paper.
Yeah.
So for the report, so you mean that we have to make it into two sections and then just put all the questions and then answer all the questions, or else it should look exactly like a technical paper? You see it? What do you mean by technical paper? It's just the format of the fonts and the references and all these things.
I am sure you have seen tons of papers out there.
I've seen papers, but I've not seen a report as a paper.
No, well, if you write your results in a paper format, the way you have seen many, and you are answering everything that I'm asking you. I mean, I wouldn't expect so that you put like 1, the answer to question 1, 2. I mean, that's a bit. It's like a recipe. It's like in a way, boring, right? So if you write something and then it shows everything that I need to see to grade the report, I said, well, this is question 1. Of course, it gives a bit more of effort on my side, right? Because then I have to find the information, the relevant information to grade it. But it also, let's say, makes you a better writer, right? Because then you find a way to write what you need to write by providing all the information that is required. So I'll let you decide. You can have 1, 2, 3 as you want. I mean, I'll let you decide. But I'm sure by now you guys have seen tons of papers, and then you know what I mean when I write these presentations of results paragraph. I'm sure you know. Yeah? Other questions? No more questions.
So is there going to be any deadline for this report?
Same thing as the other. I am not that much hardcore into deadlines. As long as you can work it out, my objective is that you guys learn. And if that requires that you take an extra couple of weeks because you had to finish some more stuff, then be it. But the danger of that, right, is that you really don't find the time because you are doing other stuff. And that is, I mean, I am not here to teach you how to manage time, right? So you are all grown-ups. You can decide when and where to do the stuff that you need. Of course, I am not hardcore on deadlines as long as you don't come in a year from now and say, hey, here's the report. Right? Then that's too much, right? But I'm not going to impose you a hard deadline. Yeah? Because I want you to learn. I don't want you to rush. I want you to think, to get the insight from the results. Look at the way I'm going to grade. I'm going to provide a rubric so that you see what I'm expecting. But there you will see that I give a lot of importance into the insight that you bring. I mean, just to put the results without providing any insight is not meaningful either. So the idea is that you get the work done, but at the same time that you learn, right? You analyze what you did, and if something did not go well, you explain what are the different possibilities, and then you try to find out. So this is the way you build knowledge, and this is what I would expect you guys do in this course. So in terms of difficulty, this class is going to be harder than the previous one in terms of the formulation and the stuff that we're going to see, right? But if you really understood what I taught you in the first one, in Advanced FEM, it's going to be a piece of cake for you because it's really not much different, okay? So if you already passed that, you know, and you understood what convergence rates are and what are the types of problems, right? And you understand that there are some problems that may have some slight singularity or some problems where the singularity is very strong. If you already passed that and you understood, then this is going to be a piece of cake. Okay? Anything else?
Yeah, just the cheat sheet. I would like to see that you upload it.
I will do that. As soon as I'm done, it's going to take me a bit of work. So I don't know when I'm going to be done with that. Yeah, definitely. I will provide you with that cheat sheet. It's a nice, I mean, it's a nice table. I'm basically compiling all the things that I normally use when I write a LaTeX document into something that I can quickly refer to. Like how many times I needed a color, for example, and I had to type on the web browser LaTeX colors, and then I go to one page that I have visited perhaps 500 times at least, to the same page. Well, that's stupid. I'm doing my own cheat sheet now. I don't have to do that anymore. Anyways, Let me stop this, and then we continue our discussion after that.